Okay, so
كم وقت عندي؟
ساعة
Okay,
عندك ساعة.
yeah.
عندك ساعة. So it's really a great pleasure to introduce Edriss Titi from University of Cambridge and also Texas A&M. And he will speak about rigorous justification of the viscous primitive equation and their global regularity. So please, Edriss.
Thank you, Nader. Thank you, Tej, for the invitation. It's a pleasure to be part of this distinguished group of participants and speakers. All right. So today I'm going to talk about the rigorous justification of viscous primitive equations. So let me start with the model that we have in mind, which is called the Bouziness Approximation. I hope you see my mouse. The Bouziness Approximation, which is, imagine that you have a layer of fluid, which is heated from the bottom and cooled from the top. So this is supposed to represent, say, the atmosphere, or maybe you can think about basically the salinity instead of the temperature, so it's diffused. But then the effect of the salinity is the contrast of the effect of the temperature, because usually hotter water is lighter, goes up, but lighter salt basically floats. So therefore, it's just the opposite effect. So here is the first equation: is the momentum balance with the Bernard approximation, and this is the buoyancy, namely that the fluid is forced by the temperature, and this is the Coriolis force because we're living on rotating earth. Rho zero is like a constant reference density. We talk about incompressible fluid, so this is the incompressibility condition, and this is the transport equation for the temperature. So it is a diffusion plus the transport plus boundary condition. Now, this problem is intimately related to Navier-Stokes. The minute we know how to show global regularity for Navier-Stokes, there should not be any problem basically showing global regularity for this particular model. Now, what do we know about the Navier-Stokes equations? So I'm just going to say something which is known to everybody here, but just for the sake of completion, in order to complete. So the Navier-Stokes equation, which is I'm looking to it, and I'm replacing now the temperature by as if it is given force. The reason is because if you look to the temperature equation here, usually if you have existence, so for short time, for sure we have strong solution, then temperature satisfies maximum principle because it's diffusion and transport, and therefore the temperature is bounded. And as a result, you can think here like as if you are forcing the Navier-Stokes with the bounded force. And what happens for this equation? So even in periodic boundary condition, we still do not know about the regularity of the Navier-Stokes. And what we know about the Navier-Stokes is a three-dimensional case: global existence of weak solutions, short-term existence of strong solutions, uniqueness of strong solutions. And the open problems until now is the uniqueness of Leray-Hopf weak solutions, even though there is a lot of attempt and work about the uniqueness of Leray-Hopf solution using convex integration, but I still did not see the last verdict about that. There is some attempt. And the global existence of strong solution. This is the background. Now we move to the fact that we live on a rotating Earth. So, and we are interested in planetary scales. You know, maybe for the PDE people, the theoretician among us that's sitting in the group, they say, oh, people talk about geophysics and weather prediction, and everybody gives a lecture about different models. What's the difference between these models? Which is the favorite model? Well, actually, models are supposed to model certain phenomena. The question, which phenomenon I would like to capture? Is it at which scales? And because we are interested in large scale oceanic circulation, namely at very, very wide horizontal scales at the scale of the planet of tens of thousands of kilometers, so we are interested, say, in large circulations. So in large circulations, you can see events taking place at very wide horizontal scales. And now this is very wide in comparison to the depth of the ocean, which is a few kilometers. And now I'm going to take this into account. So this is the phenomenon we'd like to capture, at least in the case of the ocean. And similarly, If we're interested in climate, we're interested in changes not about the weather in a local town or local county or area, but at the climate at the level of countries and continents. So therefore, in that case, we need to use the horizontal scales, which is very large. So as I said, this is some of the largest scale circulations as they are really pictured here. And this is the phenomenon, or we'd like to see the model that captures them. So as I said, this is the Rayleigh-Bénard equation. And the Rayleigh-Bénard equation, as I mentioned it earlier, now I'd like to take this equation and take into account that I'm talking about horizontal scales, which is much larger than the vertical scales. So if I really decompose the Rayleigh-Bénard into horizontal component, H here stands for horizontal. So the velocity field U, I decompose it into horizontal component and vertical component. Okay, so this is the balance of horizontal momentum. And this is the balance of the vertical momentum. And you can see the buoyancy does not enter to the horizontal momentum, but for the vertical, as here T times G. This is the incompressibility. And this is the equation for the temperature, advection, and diffusion, plus source of heat, say from the sun and from other sources of heat, whatever. So this is the Bénard convection as we want it. And now I'd like to take into consideration that talking about different scales. So as I said, the horizontal scales are the order of thousands of kilometers. Okay. Now the horizontal velocity in the ocean typically 10 to the minus 1 meter per second. The depth of the ocean is the orders of few kilometers. The rotation of the Earth, the Coriolis force, so it's one round every 24 hours. The gravity is 10, and the density of the water is, as we know it, is like basically 1 ton per meter cube. So 1,000 kilogram per meter cube. So this is the figures or the characteristics that I would like to use into consideration. Now, from this, you can take typical velocity. You take it to be the typical horizontal multiplied by the aspect ratio of the depth of the ocean for the horizontal scales. You get 10 to the minus 4, which is much smaller than U. And the typical pressure 10 to the power 7 Pascal, and typical time scale is 10 to the power 7 seconds. Now you go into the horizontal momentum, and when you do that, you basically realize that, sorry, in the vertical momentum, and therefore you realize if you substitute here typical velocity, vertical, typical time, these are the quantities 10 to the minus 11, minus 11, minus 11, 10, and 10. So you can see there's 12 orders of magnitude difference. And hence, geophysicists has no problem sleeping at night if they drop the first 3 terms, because these are the dominant terms. So these are the last 2 terms. And that's basically how geophysicists derived, or based on this kind of like argument, derived what's so-called the hydrostatic balance, which replaces the balance in the vertical momentum. And now, if I take the Bénard convection or the Bouziness approximation, and I keep the horizontal momentum as is and replace the vertical momentum by this equation, which is the hydrostatic balance, this is the system that I get, which is people usually called the primitive equations for large oceanic atmospheric dynamics. And this is the model that I would like to look, and this is the viscous case. So you can see here, this is the horizontal viscosity, and this is the vertical viscosity, and this is the horizontal diffusion, and this is the vertical diffusion. And of course, now we would like to go for the next step and try to see and play with taking into account what are the components, what are the diffusion and the viscosity coefficients, and see what happens. So this is model has been introduced by Richardson for prediction of weather in 1922. And Lyons, Timam, and Wang gave some asymptotic derivation of the primitive equation. Then the result I'm going to talk about is the result with Lee, Jin-Kai Lee. In 2000, we gave a rigorous justification of the derivation of the primitive equation from the Bénard convection or Bouziness approximation, taking into account that the aspect ratio is going to 0. I will make more comments on that, and I will mention, because there is other result prior to our result, but their convergence was usually weak convergence, namely there is subsequence that converges, but there is no strong convergence. And in this result, we talk about strong convergence. And in fact, we even give a rate of convergence in terms of the aspect ratio. Namely, it's an approximation in the classical sense, like the solutions of the Bouziness, how far they are from the solution of the Bénard, which is in some sense makes that the Bénard or the Bouziness approximation a reliable approximation. Okay, what are earlier results? So for the primitive equation, the earlier result is of Tsao and myself will show global existence of the primitive equation in 3D, even though that for the Bénard convection, we still do not know about the global existence of strong solution. This is the result. Now, global existence of weak solution has been done in previous work. I mean, we did it using Galerkin, but the referee asked us not to add it. So there was, so therefore we dropped it, and therefore the global existence and uniqueness of strong solutions. So this is the result that we know. I'm not going to talk about it. I spoke about it in previous occasions, but it's important to have it in the background. Okay. So now, as I said, here's some earlier years. As I said, Lyons and Timam and Wang gave basically the derivation and global weak solutions, exactly like Navier Stokes. There is some conditions called Z-weak solutions, which has been introduced also earlier work. Then the continuous initial data has been done by Kukavica and Pan. This was after our work. Then for certain discontinuous initial data, the result has been for strong solution has been done also. So these are like improvement. This is becoming more adding cosmetic to the theory. Once you have the breakthrough result, we try to squeeze as much as possible juice, weakening the conditions of the initial data, etc. And this basically some of these results. Now, the very first result about this is local strong solution has been given by Gonzalez, Masmoudi, and Rodriguez. This is also 2011, prior to our thing, but it's long. It's a short time existence, and we capitalize in this result in later to show that you have global existence. There is other other results in these directions, and I don't want to go and talk about all of them. So there is, for example, result of Kukavica and Zayan for different boundary conditions, and there is also a result of Hibi Kashiwabara, which is also talking about different in the LP spaces. So this technical becoming, as I said, but the breakthrough was basically by Tsao and myself. All right, so this is the background. Now, I will talk about the heart matter of our talk, namely the mathematical justification of the hydrostatic approximation. So, as I said, we're talking about the depth versus the width. This is the aspect ratio. So we talk about several kilometers versus several thousand kilometers, and therefore we would like to consider this as if it is an epsilon small enough. Okay, mathematicians basically epsilon is the number, and therefore we'd like to think about it as a small enough, and therefore we'd like to see what happens if this epsilon goes to zero. So in that sense, we need to justify the hydrostatic approximation, namely that the momentum equation in the vertical direction is approximated by the hydrostatic balance, and we need to justify rigorously these steps. So they consider the anisotropic Navier-Stokes equation, namely the Navier-Stokes equation. I'm not going to add the temperature here for simplicity of the presentation. So you have here, as I said, the horizontal viscosity and the vertical viscosity in a thin domain. So M is the horizontal domain, and 0 epsilon is the thin domain, which is basically like the ocean, if you like to think about it. Epsilon is the width of the ocean in comparison to M, which is of order 1. See, M is like order 1. So we look for the velocity U, which is V and W. V has two components, V1 and 2, V2, and M2 is a domain of order 1 in R2. Now, we're going to assume that the horizontal viscosity is order 1, and this is reasonable based on physical ground. I don't want to talk about it. And the vertical viscosity, epsilon square, this is more or less reasonable, but mathematical assumptions, because the exponent square here was for our earlier result, and then one can really play with that, changing the exponent and see what we can get, and I will talk about that later. But it's reasonable to assume that the vertical viscosity is small relative to the horizontal viscosity, And now we rescale. We call V epsilon. We rescale the velocity in the z by epsilon z, and the vertical velocity by 1 over epsilon and epsilon z, and the pressure like that. Now I would look at the rescale the Navier-Stokes equation. So the scaled Navier-Stokes equation, it's exactly the original equations, but now taking epsilon into account using the scales that I introduced, but now is in the domain m and 0, 1. Namely, now the domain is no longer thin, it is of order 1. And now I would like to investigate this problem in this interval. Of course, it's the same like Navier-Stokes equation. Okay, the same like Navier-Stokes equation. And there are some results about Navier-Stokes equation in thin domains in which people prove, like say, a global existence for data which is large enough depending on the aspect ratio, or namely depending on epsilon. Okay, this is a result of the original result by Geneviève Rogel and George Sell, and the later Timam and Zayan, and so on and so forth. But that's not the line of, or the direction I'm going to. The idea is to look for the formal limit when epsilon goes to 0. So this disappears. So therefore, V epsilon, U epsilon, P epsilon formally will converge to some V, W, and P. We need to show that there is this limit. And then formally, the limiting equation is this equation, which is exactly the horizontal momentum as is, the incompressibility. And now, because this is disappear, we get dP dz is 0, which is the hydrostatic balance. Notice that there is no temperature in this equation. For simplicity of the presentation, I said I'm going to drop the temperature. So this is actually the primitive equation, which is the formal limit of this, as we would expect. And now the idea, what is the result that we have? So as I said, formally, when epsilon goes to 0, we get this particular system. And now here is the result, the first result. I'm not going to go about technical because usually in conferences, if you start going technical, I mean, people do not get much out of it. This is all written in the papers, and usually we try, or at least papers that I'm co-author, I try to put as much details, and to the point that sometimes the referees ask us to cut some of these details. But that's why we give it, so at least the referee can see that we have the complete details and we can justify them. So therefore, one can really go to the papers and check the situation. So also check the proof. So what is the result? So the theorem here is given periodic domain. I mean, at least for the periodic boundary conditions, that's what we have. V0 and H, this is the horizontal velocities in H1, such that this is the condition that needed, which is like we call it well-prepared initial data, because this is the condition for the primitive equation. We need that for the primitive equation because I want them to have the same initial data. And without loss of generality, we assume that the average is 0. Let V epsilon, U epsilon, and VW respectively, the first one is an arbitrary weak solution of the scaled Navier-Stokes equation. We know that the Navier-Stokes equation does not have unique weak solution. Okay. Now people say, oh, but the initial data in H1. No, only the horizontal component in H1. The vertical component is actually only in L2. So therefore, only what we can talk about is weak solutions for Navier-Stokes. So because I don't have uniqueness, so we consider arbitrary weak solution of the Navier-Stokes equation with the well-prepared initial data. But for the primitive equation, for such initial data, this is the result of Tsao and myself, we have global existence of unique global solution. So this is the unique global solution of the primitive, and the epsilon to epsilon is any weak solution of Navier-Stokes equation with the same initial data. Okay, then we have the following convergence result, and I call strong convergence because there is earlier result by Bresch and collaborators in which they show there is subsequence converging weakly. Okay, here we show that the solution of the epsilon U epsilon converging to V0 in L infinity in time, L2 in space, and the gradient of the epsilon gradient of W, U epsilon converging to gradient of V0 W in L2, and the rate of convergence is of order epsilon. This is the new addition into this particular result. So in other words, if you have a strong solution for the primitive equation, and you take any weak solution with the same initial data, there is sort of tube in these topologies, okay? There's tube, these topologies around the epsilon, that all the weak solutions of the Navier-Stokes equation emerging from the same initial data must lie in this tube, and the width of this tube, or the diameter of this tube, is order epsilon. So therefore, all the solutions of the Navier-Stokes are within the vicinity of the primitive equation solution, all the weak solutions. This is the first result. So now, what about strong solutions? So what if we demand the initial data V0 and H2? If V0 and H2, then the well-prepared initial data, also the W0 for the Navier-Stokes, namely also the vertical component will be in H1. Aha, because V0 and H1 and W0, sorry, because V0 and H2 in particular is in H1 and W0 is in H1, then we talk about strong solutions for Navier-Stokes equation. Okay, so now having this into account, and again, let V epsilon, W epsilon be the, and V be respectively the unique local strong solution of Navier-Stokes, because now the initial data is in H1, so I have short time existence of Navier-Stokes equation, strong solutions, and the unique solution of the primitive equation. So for short time, I have Navier-Stokes for this initial data, but the primitive equation I have a global with the same initial data. Then, and here is the result. There exists a positive number epsilon depending only on the H2 norm, and this is in some sense in the it is in some sense it is related to the thin domain result of Rogel's cell and Timam and Zayan, because you see the thickness is depending on the initial data. They formulated dually, namely they said the initial data depending on the aspect ratio when it is small. Now we'll do the opposite. So such that for any epsilon between 0 and epsilon 0, the strong solution of the Navier-Stokes, not only exists locally, but globally in time. And we have also the following strong convergence, namely this is converging to V0 in this topology, and the same, and relatively this is converging in this topology. And now we have W epsilon converging to W in this topology. And again, the convergence rate in these topologies is also of the order epsilon. So this is the result about justification of the primitive equations as a limit, not any longer formal, but exact, and we have precise conditions about the rate of convergence. Now, what happens if I look at the primitive equation with only horizontal viscosity? Okay, and the diffusion. So do I know anything about existence and uniqueness? And indeed, this is a result by Cao, the Chongqing Cao, my former, he's like the guy with whom we had the primitive equation. And again with Jin-Kai Li, we prove a global regularity of the primitive equation with only horizontal viscosity. We don't need the vertical viscosity anymore, and with horizontal diffusion. So this system, namely, there is no vertical viscosity and no. As I told you, the vertical viscosity is smaller than the horizontal one. So what happens if we drop it completely? What happens in this case? We first prove that the primitive equation has a global regularity, because the whole idea, this would be the reference solution that I would like to compare against. So here's a new result, which is just appeared in Journal Differential Equation, again with Jin-Kai Li and his student Yuan, in which we have the following result. When the vertical viscosity scales like epsilon to the power alpha minus 2, for alpha bigger than 2, okay, then the solution of the scaled Navier-Stokes equation also converge to the primitive equation, but now the order of convergence is epsilon to the power power beta, where beta equals 2 minus alpha minus 2. And this is different than the case that we have earlier with Jiang-Kai-Li, okay, which is I mentioned earlier. So this is, in some sense, is a stronger result, but the proof of this result is completely different than the previous one. Therefore, the two results complement each other, not one included in the other. And because the techniques used are different, we can get like a good convergence rate that we would like to expect for both results. So this is when we talk about, instead of the vertical, the viscosity scale like epsilon to the alpha minus 2 instead of epsilon squared. Sorry, there's a typo here, alpha equals to 4. Okay, when alpha equals to 4, that's the result with Jiang-Kai-Li. So this is a different thing, and therefore you get different convergence rate. Again, this is just appeared in the journal of differential equation, and one can go to the details and see them either on arXiv or on in the published. Okay, now I'm going to move into results about atmosphere. Okay, so it's again, the primitive equation will be the same equation that model the momentum. But now we know in the atmosphere, because as I said, I'm interested in the equation, which is like Bouziness, namely the Navier Stokes coupled with the temperature. Now in the atmosphere, you can think about it like it is heated from the bottom by the ocean and cooled from the top by the stratosphere up there. Now people says heated. I mean, I never thought that the ocean is like source of heat. What's important in science, we always know, is the difference. You know, for example, if two people know exactly the same knowledge, they cannot have an exchange. Nobody can add anything to the other. Only when there is a difference in knowledge, then there is an exchange. Whatever I know, I pass to you, and whatever you know, you pass to me. There is an exchange. So we need difference. So the temperature in the up there is like minus 40 or something like that, or minus 30, and the temperature of the ocean is the orders of like between about 15 Celsius. Therefore, there's a big difference between the temperature, and therefore we can think about it that it is heated from the bottom and cooled from the top. This is the usual Bernard convection. However, in the atmosphere, there is moisture. And because there is moisture, there is vapor. And therefore, the thermodynamics enters here. And one has to, in some sense, take this into account because, you know, the vapor, when it is hot, it takes some of the temperature. And when it is cooled, when it is condensed, then it releases some temperature. So there is other source of temperature than the bottom, namely heating from the bottom and cooling from the top. And that's what we would like to take into account here, coupling the primitive equation with this microphysics of the thermodynamics of the moisture. So now in the tropics, it is known that in the lower troposphere, the velocity, in some sense, the wind in the lower is equal in magnitude, but opposite sign of the upper. So it's almost like shear flow. And because this looks like shear flow, so therefore one can really approximate the first baroclinic mode, namely the first mode, which is depending on x and y and z, to be like cosine phi z, okay? Because this is a function which is almost like shear. Therefore, you take only the first mode. You don't take higher frequency, you don't have like oscillation because it's not really going back and forth. It's just basically almost like going in one direction. So for the study of the troposphere extratropical interaction with the transport momentum between the barotropic and baroclinic plays an important role, it is necessary to retain both the barotropic and the baroclinic modes. In other words, I'm not going to talk about the primitive equation fully. I'm going to butcher it. I'm going to truncate it. I'm going to use only part of the baroclinic mode and the full barotropic mode and see their interaction. Now, so because of the above, we impose the following ansatz. So the velocity field and the pressure are the barotropic mode, namely the average in the z direction. So it's a function of two variables. and the baroclinic mode, which is basically the rest. So this is the coefficient of it, but I take only one Fourier mode, only the cosine. I don't take cosine 2 and cosine 3, cosine 4, because as I told you, this is what dominant in the velocity field based on measurements. So therefore, one look for ansatz, I look for solution of this type, and then the corresponding W will be given by that, which carries the barotropic first and baroclinic mode, which are unknowns. So now the unknowns will be U and V, but both of them are function of X and Y. It's not function of three variables because I truncated and took the dependence on Z to be only cosine here and sine there. Now what happens here? So indeed, performing Galerkin projections and really severely projecting. So Frierson, Maida, and Paul Louis, in 2004, they reached to the following model. This is the barotropic mode, but then it is forced by stresses coming from the baroclinic mode, and here is the V, this is the V here. Incompressible, and this is the baroclinic mode, which is coupled with the barotropic mode. And now the temperature is again the same temperature, but there is a source of heat, and this is the source of heat which we'll talk about later, namely what is the source of heat, where the heat coming, and that's what I would look at the coupling to the temperature. So this is the model that we'd like to look at. Notice that I put the plus with red sign, because if this was a minus sign and I look at the first two equations but drop the temperature, this would be exactly the 2D MHD equation, where V is like the magnetic field. And therefore, with viscosity, we know that you have a global existence and uniqueness. So let us see what you're having. So this subsystem looks like the magnetohydrodynamics equation, but div U equals to 0 is not preserved, namely the div of B is not preserved. Many people make mistake when they write the magnetohydrodynamic equation. They write the system and put div of B equals to 0. That's not really correct. Div of B is not an extra condition. There is no pressure in the magnetic field. What happens is the divergence of the initial data is 0. And then one can show, if you have nice solutions, the divergence of B is invariant. And because it's initially 0, it remains 0 all the time. So it is part of the solution. It is not part of the equation. So now, in our case, because of the plus sign, one cannot really show that div of V is invariant if it is initially 0, and therefore we cannot look at this as MHD equation, and indeed the baroclinic mode is compressible. So in other words, this subsystem is like linearized compressible Navier-Stokes equation. Now the corresponding inviscid system, one has a derivative loss, because here I have div of V. In here, I lose one derivative in this equation, and therefore this is a little bit more tricky. All right, so what is the situation? Now, what about the source of heat? So if you have moisture, Frierson, Maida, and Paul Louis added that if you have a moisture, the equation for the moisture is advection, okay? And there is some other parameters, particular source of the moisture, which is the precipitation. And the precipitation is involving a fast scale, namely Q is the moisture. So if you are above certain critical value, that's why the plus sign, namely it is when it's positive, it is different than 0, and when it's negative, it is 0. So when the precipitation, when the moisture is too small, below certain critical value, then this precipitation is 0. Okay, therefore there is no source, or loss of moisture. However, when they becoming too high, then rain occurs, and this triggers very quickly at rate 1 over epsilon. So switch very, very quickly, and therefore you lose moisture from the atmosphere. Anyway, without getting too much to the physics, I just basically want to tell you that what's the microphysics in here. So without getting into the physics, so this is the model for the moisture. And now we know that moisture is, when condensates, it releases temperature. So putting all these things together, Fraser and Maida looked into, this is the momentum equation coming from the truncated primitive equation, exactly the same. And this is the temperature now. This is the buoyancy. TE is the equivalent temperature. So this is the temperature which has some source from the, and QE is the equivalent moisture. So therefore the equivalent, the Q is adding to the temperature. So the temperature has some kind of like part because it's the equivalent temperature is not the original temperature. This is TE minus QE is the original temperature. So TE is not like the temperature. So there is a contribution from the moisture to the temperature. As we know, when it rains or when the moisture condensates, therefore it releases heat. And this is the equation for the moisture, which is again with the precipitation taken into account. So this is the model that one would like to understand and investigate. And it is not like the MHD because there is the plus sign. So the div V is compressible, is not zero. Div U is equal to zero. Now, what happens to the relaxation limit? Because we're interested not only in this system, we'd like to know what happens when epsilon goes to zero. Why? Because if you'd like to integrate this system, you have a time scale 1 over epsilon, means that the delta T has to be very small. And now if we know what's the limit equation, I have an equation without epsilon, which is maybe I can really simulate more efficiently. And then if the solution of this equation, which depends on epsilon, is close enough to the equation when epsilon goes to zero, then the simulated one is approximating reality. So that's why we usually interested what happens when a parameter goes to zero, because usually for numerics and for computations, it is much more difficult because we need time scales delta T to be very small. All right, so what happens now? Now, what happens is that notice that the right-hand side is always non-positive. And therefore, without much effort, as epsilon goes to zero, it doesn't matter because the right-hand side is non-positive, then you will have at the limit, you get basically not a differential equation, but differential inequality when QE is less or equal than zero. And only when QE is strictly less than zero, you get equality. So you get this kind of like crazy system, which is coupled differential equation with differential inequality. And this is the formal limit system. Now the question, does this system has existence and uniqueness? And does the solution of the original system converge to it, and in what sense? All right, so result concerning this model. So the first result was investigated by Maida and Souganidis when they looked at the implicit case, but at the linearized version, not at the fully nonlinear system. And they showed that indeed that there is existence of the limit equation, but without really a convergence result. Now, together again with Jinkai Lee, we proved the global well positiveness of the system with epsilon and of the limit system and uniqueness. You see, showing uniqueness for a system like this, because you have an inequality is by energy method is not really an easy task because you cannot compare two solutions because the difference, I don't have zero on the right hand side. One is negative, the other one is negative. The difference, we don't know what to decide about the right hand side. But anyway, so we prove uniqueness also for this limit. And in fact, we can also show the explicit rate of convergence of order square root of epsilon. So this is the other result that we have concerning this specific model. And now I would like to continue and talk about moisture model for warm clouds. As I said, now I would like to go more into the microphysics and not talk about only the mode of Maida and the company, namely when they look to the truncated primitive equation, but I would like to take into account the full primitive equation and as much as possible full physics. So in the cloud formation and the moisture. Now we know the microphysics of clouds is extremely complicated and extremely complex. How so? Because as we were kids in the science class, even without getting into thermodynamics, they told us that matter can find itself usually in three situations or three status. Either it is gas or liquid or solid. And there is this critical point where all the three phases meet, and anybody who really learned some physics and thermodynamics knows that this is really very complicated. Transition from one side to the other is okay when you have a curve, but at near the critical point is very complicated. And unfortunately, or fortunately, depending how you want to look at it, this is the situation in the clouds because water or find itself in three states. Either it is vapor, or it is water like drops, liquid, or it could be ice, and therefore it's solid. And hence the microphysics is very complicated. So when I'm looking here, we're looking at moisture model for warm clouds. By warm clouds means that we're looking at them without the ice phase. So only when they're involving the two phases of liquid or vapor. Okay, and that's the model that I'm going to talk about. Okay, so what happens is that the density of rho J divided by rho D. Rho D is the density of dry air, and this is the density of the air or the liquid or the vapor, which is in vapor state or condensated state or rain. Okay, so this is the QJ. So what happens is that if you have water vapor, now if it is condensated, so when it is larger than some critical value, then it becomes cloud water. So QC is cloud water. QV is QV is vapor. Now, cloud water, there is something if becoming too much, so above certain critical value, then it turns or transforms into rainwater. Now, while rain is coming down, so when QV is smaller than this, there is some evaporation, and therefore there is conversion back into water vapor. And therefore you have this cycle that one has to model in some sense, that some of the rain doesn't reach us on Earth because it evaporates before it reaches us, and this comes here. And then it condensates, and when it's above certain critical, becomes water, cloud water, and it is either too heavy, then it becomes rain. This is the microphysics, and this is not the purpose of this conference, but I wanted to tell you where the models are coming and what we are trying to model. And we know that in this process, when you condensate, the moisture release heat, so it contributes to the temperature. Okay, and here when it evaporates, it needs heat, so it takes heat from the environment, and therefore it affects the equation of revolution for the temperature. Okay, without getting much into details, as I said, these are the sources for the different phases, and you can see this is when I say QVS, this is a quantity minus QV. That's when I say when you are above. Notice that when I am above certain value, that's what happens. When I am up below certain value, that's what happens. When I'm above certain. So this will be modeled by the plus function. It is 0, or when you are above, then you take that into account. And this is manifesting itself by these quantities, QV S minus QV plus. So when this is negative, it is 0. So there is no source into the evaporation, and so on and so forth. That explains where these kind of like terms coming from. And now, what are the equations that we have into here? So this is the transport of the vapor with the sources that I mentioned. This is the evaporating part, this is the condensating part, and this is a diffusion. And the diffusion here is given by this operator. It's the horizontal diffusion, but the vertical diffusion has some weight. It is, which depends on P. And now what's P? Here in this model and in the atmosphere, people replace the Z, the height, by the pressure because it's more realistic for modeling what's happening. So P, the pressure, because the higher you are, the lower the pressure. So instead of talking about Z being the variable, P is being the variable, namely the pressure. So this is the diffusion part, and similarly for the cloud water, QC, and for the rain water. And these are, as I said, the sources. And this is the temperature equation. Again, is the transported plus there is something. This is coming from the rain part. This is the omega. This is coming down, and this is the right-hand side, which is again the source for the temperature. I said when things condensate, you release heat, therefore the temperature increase, and when you evaporate, you take heat. So that's why this is with minus sign, and therefore it would be with minus sign. Okay, so this is the model for the temperature. And now, as I said, there is a transport part, U, V, and omega, or W. This is supposed to be W, but we call it omega. This is traditionally in this field, because W is when you take function of X, Y, Z. When you move into the coordinate U, V, and P, you call it W, or you call it, sorry, omega of X, Y, and P. All right. So this is the model that we have into account. And now we would like to check what's happening with this model. So this is, again, I'm assuming that this is the domain. It's between P1 and P0, and M prime is a bounded domain in R2 with boundary conditions which are really given here without getting into the details. And now here is the result. So the first result we have said, okay, can we study this model when you give me the velocity? So I don't couple this system to primitive equation or Navier Stokes. You give me a velocity field. Can I show well posedness for this sort of reaction diffusion system, but not really traditional, because there is this switch function, sorry, the pluses, this function, sorry. It's not exactly reaction diffusion because it has these particular terms. Notice in particular this term, which is Q plus beta, when beta between 0 and 1, and this is causing problem because it's not Lipschitz to show the uniqueness and so on and so forth. So this is not really a straightforward reaction diffusion system. So given the velocity, what we can show, and this is the result what we have with the Sabine Hetmeyer, Rupert Klein, and Jinkai Lee. We show that if you give me the velocity in this space, and it's incompressible, and this is the conditions, then you can show global existence and uniqueness of solution for the microphysics, namely for the moisture equation coupled with the temperature. This is the first result. And as I told you, one of the issues in the uniqueness is that in the vapor part, there is rain part to the power beta, and beta between 0 and 1. And therefore, this shows some problem with the uniqueness. The trick that we have, and again, just to tell you how we overcome the problem, again, you have to read the paper to see the details. We change variables. We call capital Q, QV minus QR, and H like this. And then when we do that, then we get an equation in capital Q, in QC, QR, and H. And the right-hand side will be involving QR plus only, but one can take advantage of the fact actually that it should be QR here plus. The QR plus beta is a monotonic increasing function, And therefore, when you talk about uniqueness, when you compare two solutions, this product is positive, therefore you can drop it. You don't need to do estimates on that. So use the monotonicity of that. At least this is the trick that we capitalize on to show the uniqueness for this model. All right, so the microphysics, when it is given temperature or when give it velocity, you prove global existence and uniqueness. This is the result that we have. Now, what happens if I coupled it to the primitive equation? Now we do mathematically the usual thing. You give me the velocity field, I've solved the microphysics, the moisture, and this gives me in particular the temperature. Now, if you give me the temperature, I go back to the primitive equation, assuming the temperature is given, and then I have a global existence for the primitive equation by the result of Tsao and myself, and this gives you a new velocity. You take the new velocity, which is it has to be in the right spaces, and then you solve again for the microphysics with the new velocity, and then you show global well positiveness. Now this gives you a new temperature, and you go back to the primitive equation with given a new temperature, and you solve it again, and then you have iterative scheme, and then you show that this iterative scheme is converging, and this is the other result. So when we talk about coupling the microphysics to the primitive equation, so given the initial data in these spaces, and the temperature and the moisture is in these spaces, and they are all non-negative because this is concentrations, then one can show that you have global existence and uniqueness in time of the coupled microphysics to the primitive equation. Now the velocity is not given, it satisfies the primitive equations, as I said. This is a lot of work, but nonetheless, as we said, we did it in two steps. One, given the velocity, and the other one, then we capitalize on the work with Tsao and myself. Okay, there's some other works about the primitive equations with the moisture for different models of the microphysics, different microphysics, a little bit simpler, but again, there's some work which is earlier done by Kotizilati, Wang, Kukavica, Timam, and Ziyan. Now, because we talk about the atmosphere, and now we are basically here toward the end of my lecture. In the atmosphere, many times geophysicists tell us, wait a minute, in the atmosphere, taking the air to be incompressible is not very realistic. And in fact, one has to look into the compressible Navier Stokes rather than the incompressible Navier Stokes. And of course, you have to couple it to the temperature first, as we did with the Tsao. And then, so there is a scientific program that I've been carrying out with my former postdoc, Xin Liu, about this particular thing, trying to see what we can do about the compressible primitive equation. So first, we can show global existence and uniqueness of compressible primitive equation for small data. This is expected in the compressible case, that you cannot maybe show global existence for all initial data, but at least for small data, the primitive equation, namely, we have to write the vertical velocity in terms like you need to use in some sense the equivalent of the hydrostatic balance, and in this case, recovering the W from V is not an easy task, so one has to really work. So this is part of the modeling here. So we prove that. Then later, we look at the Navier-Stokes, compressible Navier-Stokes equation, and see, does it converge to the compressible primitive equation as the aspect ratio goes to 0? This is the equivalent result that we had, that I mentioned earlier, that we have for the incompressible case with Jin-Kai Lee. And we can show that again for small initial data as the aspect ratio goes to 0. The next thing is, do we have convergence of the compressible Navier primitive equation to the incompressible primitive equation? Now notice, the incompressible has a global existence. The compressible, as we have shown, it has global existence uniqueness only for small data, or you can have short time existence for large data. But now as Mach number goes to 0, we can show this result. In particular, similarly, and we have also the rate of convergence in terms of Mach number. And in particular, one can show that if the initial data is well prepared of the compressible primitive equations, then it converges to the primitive equation. Now, the question, can we look into other kind of distinguished limits? And this is a work in progress. I think my time is over, and I would like to thank you for your attention.
Okay, thank you very much, Edriss, for a very nice talk. Are there questions? Are there questions or?
I might have an elementary question.
Yes, please.
So why do we need to study the rate of convergence? So if we already proved the existence and uniqueness of the problem, why is it important to study the convergence of epsilon, the rate of convergence of epsilon to 0?
Very, very nice question. As I mentioned earlier, that why do we study the limit to begin with? Okay, at least this is point of view. I mean, like there's maybe other reasons, but at least, as I said, if you have a problem which has epsilon small, and you would like to do simulation, then this is restrictive in your numerics, and this will basically require something called high conditional number. Namely, you need to take your mesh, your time step or your spatial step very small, and this is difficult. It needs a lot of memory and difficult to simulate, and therefore you would like to see what happens as epsilon goes to 0, because epsilon is very small. Hopefully you have a nice model at the limit, which has also nice property, existence and uniqueness. And now the limit system does not have epsilon in it. And therefore simulating it maybe has other features and other problems numerically, but at least the epsilon problem is removed. And therefore this does not restrict the time step, and the mesh, the spatial mesh, doesn't have like high conditional number as in the original system. And now you can simulate the limit system. But real world is with epsilon. Reality has epsilon in it.
Yeah.
And therefore, I would like to approximate reality. Aha, the simulation of the epsilon equals 0 give me a solution. Now, how far is this from reality? That's why I need to show that the real solution and the limit solution are close, and how big is the error in order to get something reliable. I mean, many people study these problems without stressing this point, which is fine. At least this is one point of view. Maybe there's other reasons for studying limit behavior, okay? And I mean, like people can tell you, for example, why in Boltzmann equation, why we need to study that Boltzmann is converging to Navier, Stokes, and Euler. Who cares? Why don't we go to Boltzmann and simulate Boltzmann?
Yeah,
It is nearly impossible. However, we know that under certain conditions, the solutions of Boltzmann converge to Navier, Stokes, and Euler. Whether there is error estimates, that's a different story. And therefore, simulating Navier, Stokes, and Euler may be still more realistic at the moment for the computational power. And hopefully, if you have some error estimates, then you can say, I am approximating reality very nice. That's, I think, is one of the main reasons for even studying limit system. In perturbation analysis in general, singular perturbation analysis in general is the same. I believe similar problems. I've been discussing this with many people. Why we care about in the incompressible case, why we care about studying Euler equation. In reality, we have viscosity. Nobody can tell me there is no viscosity in the world. Nobody. I mean, like this. Otherwise, we have the well-known paradox, what's his name, French guy, I forgot now. I'm getting old, or it's Alzheimer, I don't know. The paradox that basically airplanes cannot really fly, or so anyways, without viscosity, there is paradox. So you need viscosity. So in reality, there is viscosity. However, for high Reynolds number, namely viscosity is very, very small, then again, if you like to simulate Navier Stokes, it is ill-conditioned. It has high condition number. You need delta x to be very, very small and delta t to be very, very small to be able to solve. And it's prohibitive for numerics. Now, the limit equation Euler, at least formally, has no viscosity in it. And therefore, I don't need to worry about the viscosity issue. I have maybe other issues to worry about numerically, but at least this issue has been removed. And now, if I can simulate Euler, and I can show that solution of Euler are close to the solution of Stokes, namely to reality, then I have done the job. And if I can even error estimate how far solution of Euler from solution of Stokes in terms of the viscosity, I can tell you how close I am to reality. Otherwise, I really do not see many reasons of why we need to study Euler. I mean, like, why do you want to study Euler? No, if it's not limit of Navier-Stokes, and then I need it for numerics or for some other reasons because it's easier or it has some features, which is we can really study about Euler that we cannot study in Navier-Stokes. But if the solutions are closed, then we are in good business.
Okay. Thank you so much. Thank you.
Okay, are there other questions?
Yeah, actually, Amjad, they told me, thank you, Amjad. Yes, he told me that it's called the Dalambar Paradox. Yes, I forgot the name. I knew it's French, Dalambar. I'm just forgetting many things these days. So thank you, Amjad. So it's the Dalambar Paradox, that namely, without viscosity, the total lift on he took sphere and he take flow past the cylinder and look for solution of Euler, and then in that case the total lift was 0 that he calculated. The difference in the pressure is 0, and therefore there is no lift. The sphere does not go up. But we know that in the airplanes fly and the birds fly because of the viscosity. Thus he thought that this is what's called the Dalambar Paradox. Without viscosity, airplanes and birds cannot fly, even though it's very small viscosity, but you need it. Or maybe there is some effective viscosity because of the eddy viscosity because of turbulence. That's a different story, and I don't want to get into that direction because that's not the purpose of this conference. Or maybe it is actually. This is the center for turbulence as well.
Mr. Nader.
Okay, other questions?
I have a technical question.
Yes.
About convergence of a local solution to global one.
Yes, about the primitive equation you're talking.
The V epsilon is the global solution of Navier-Stokes equation. Would you like to explain me the convergence of V epsilon local solution to the global one V of primitive equation?
Yeah, I understand what you're saying. Let me just, I will tell you what's the idea
Yes.
behind it. It's a very simple idea. I mean, I'll go back here to this particular one. Okay, let's look to this one. Okay, so
Yes.
what happens is that Navier-Stokes has short-time existence.
Yes.
Primitive equation has a global existence.
Yes.
Now, if you show that for short time, the solution of the Navier-Stokes remains close like epsilon to the primitive equation, therefore the solution of Navier-Stokes at short time did not become too large. And therefore, you can extend it for a little bit more. Now, it remains close to the primitive equation within epsilon. Therefore, it does not blow up. I can extend it further and further, and that's it. It is basically a marching process. It is the approximation result for short time that you capitalize on to show the global existence result.
Thank you.
It's a very simple idea.
Okay, more questions? Any more questions? Or it is just a very rapid question before we move to the next talk. Like, when you have that model with moisture, with the moisture, what do you have, like particular solutions that maybe model rain, or like some? Okay, I mean, I see the equation and okay, you explain it, but I mean, by just looking at a solution, can you say, okay, this is a solution where we have some rain happening or something like that?
Well, I mean, are there particular specific solutions for this kind of like equations?
Yeah, exactly. Are there a particular solution like a traveling wave?
Yes, for example,
like traveling waves.
Yeah, is there some particular solution you would like to study if they are stable, unstable, and so on and so forth? I believe
right.
You guys in Abu Dhabi, actually, in Abu Dhabi, you are supposed to be able to answer these questions. You have the center that in atmospheric that MIDA was established, and MIDA was and let's say the dynamo behind this project and this program. And now the people in NYU and Courant, they are doing things. So I think maybe Bolem, whether Bolem, whether he could be the person to answer this question. But I probably most of the time when they study such situation, I would say they would simplify it further. For example, I mean, MIDA and Suganidis, or MIDA and his collaborators with Frierson and Paul, they look to this even more simple model rather than the full spiel, the full thing, for very simple precipitation. And maybe for such equation, for this particular model, which is even simpler than the original one, maybe one can really have particular solutions. You understand what I'm saying?
Okay.
Yeah. Now you have to go for even.
I mean, I thought you may have thought about these things, and
no. Well, I mean, we are still we just I mean, like the paper about this model. It's just very new, and
okay.
I mean, getting into all this. I can tell you, I mean, everything is recorded. I don't know if it's going to be stopped recording, but seemingly, still the mathematical analysis, the applied analysis community did not really got attracted to geophysical models. And sometimes there are difficulties finding the right mathematical journal for publishing, So therefore, going to this specific solution for that particular model, traveling, it needs particular people of interest. You need some people to be interested in these things, write referees, and so on and so forth. And so either you go to the geophysics journals and say, this is too mathematical, I don't want to study solar spaces even now. Or if you go to the PDE mathematical journals, usually says, well, that's too specific, too narrow. I mean, like what, so, but nonetheless, this is good. We're doing science, but I'm just basically mentioning on the side some of the issues that people might face in the geophysics community in applied analysis. But slowly, some people are moving and getting interested in these kind of like models. I mean, people, because the real problem is Navier Stokes. That's what people focus on. But coupling it with moisture, I mean, like say, okay, well, I mean, that's a second order problem. I hope this answers your question with some little bit twist into it. But if Boulam comes to visit in Abu Dhabi, ask him.
Yeah. Okay. Okay. Are there other questions? Other questions? No. Okay. Thank you again, Edriss. Thank you very much.
Thank you again.
And then we'll.
For the invitation.
Yeah, thank you. Thanks a
Thank you
lot.
for the invitation. Thank you all for your attention.